Which of the following are second-order linear homogeneous recurrence relations with constant coefficients? Now, here I have the definition of a second-order linear homogeneous recurrence relation with constant coefficients from the textbook, which says it's a recurrence relation of the form a sub k equals a constant, a fixed real number, a times a sub k minus 1 plus a fixed constant b, which has to be non-zero, times a sub k minus 2. So this reminds me a little bit about Fibonacci sequences. The Fibonacci sequence is specifically a second-order linear homogeneous recurrence relation with constant coefficients where those constant coefficients are both 1. So a equals 1 and b equals 1. That's the recurrence relation for the Fibonacci sequence. So the only difference between these types of sequences and the Fibonacci sequence is that we're allowing different types of coefficients, but b has to be non-zero. Let's start with part A. So if this were a second-order linear homogeneous recurrence relation with constant coefficients, we should be able to determine what a and b are. So a is the constant coefficient in front of the a sub k minus 1, which in this case is 2. And b is the constant coefficient attached to the a sub k minus 2, which is negative 5. And so using this definition here, part A is a second-order linear homogeneous recurrence relation with constant coefficients. Now, if you notice in part B, we have a little bit of an issue here. This k here is something that is determined by the value of the index variable. And that's not allowed in what's supposed to be the position for the constant coefficient, but it has to be a constant coefficient. In this case, k is not constant because k is the index variable. And so this is not a second-order linear homogeneous recurrence relation with constant coefficients. For part C, we have c sub k equals 3 times c sub k minus 1 times c sub k minus 2 squared. Now, this multiplication really ruins everything. There's no way to salvage this or rewrite this in a way that's clearly a second-order linear homogeneous recurrence relation according to this definition here. For part D, d sub k equals 3d sub k minus 1 plus d sub k minus 2. In this case, we can pick a equals positive 3 and b is just 1. And in this case, b is non-zero. These are constant coefficients, so this is a second-order linear homogeneous recurrence relation with constant coefficients. Now, part E and F are a little bit tricky. Let's do part E first. R sub k equals r sub k minus 1 minus r sub k minus 2 minus 2. Now, it's really important to understand the difference between a constant coefficient and a constant. A constant is a number by itself. It is a number that represents a term by itself. So it's not actually multiplying by anything. It's just a number by itself. Whereas a constant coefficient is a number being multiplied by something. In this case, the constant coefficients are numbers that are being multiplied by either the a sub k minus 1 or the a sub k minus 2, or in this case would be the r sub k minus 1 or the r sub k minus 2. So this is not a second-order linear homogeneous recurrence relation with constant coefficients because, by definition, we're not allowed to have constants within this recurrence relation. We're allowed to have constant coefficients, but not constants. Part F is really tricky because if you notice, there's only one term here. But if you look at the definition of the second-order linear homogeneous recurrence relations with constant coefficients, there are two terms. The key, though, is that even though there are two terms in this definition, A is allowed to be 0. There's no issue with A being 0. There is an issue with B being equal to 0. B cannot be equal to 0 according to this definition, but A can equal 0. So what we can do is we can say for part F that A equals 0 and B equals 10. This satisfies the definition of a second-order linear homogeneous recurrence relation with constant coefficients. Anyways, thanks everyone, and I'll see you in the next video.